Alright, so in this video I'm gonna be explaining another important paper with the title Theoretically Improving Graph Neural Networks via Anonymous Walk Graph Kernels. This www paper in 2021. www 2021. Graph neural networks have achieved tremendous success in graph mining. However, the inability of GNNs to model substructures in graphs remains a significant drawback. Specifically, message passing graph neural networks as the prevailing type of GNNs have been theoretically shown unable to distinguish or detect or count many graph substructures. While efforts have been paid to complement the inability, existing works either rely on predefined substructure sets, thus being less flexible, or are lacking in theoretical insights. So, we propose GSKN, a GNN model with a theoretically stronger ability to distinguish graph structures. Specifically, we designed GSKN based on anonymous walks, flexible substructure units, and derive it upon feature mappings of graph kernels. We theoretically show that GSKN provably extends the 1WL test So substructures are very important in graph classification. For example, one tool is graph mining, graph kernels. And the graph kernels can be defined in many different ways. For example, you can use walk and path kernels. For example, this is an LWalk kernel that compares all length LWalk starting from each node in two graphs. Another type of good kernel is WL sub-3 kernels, which is a finite depth kernel variant of 1WL test. So a WL sub-3 kernel of depth L compares all sub-trees with depth less than equal to L, rooted at each node. So in reality, when node attributes X are of continuous values, we may replace the hard delta by soft relaxation. And then anonymous walk is another important tool that we can use to capture the structure. And we formally extend AWS to form of GKs. So we design L anonymous walk graph kernels. So the graph kernel is using the idea of L anonymous walks. So we combine here kernels and yield anonymous random walk kernel. We call it ARGK. Combining the two kernels, the walk and the anonymous walk, if you concatenate them, then you have a kernel that is a combination of the two kernels. And now that we have the kernels, we can go to graph neural network for anything you want, like graph classification, any task you want. For example, psi of Gauss is the kernel mapping of Gaussian kernel. And I have a video about Nystrom method. It aims to project points from an arbitrary reproducing kernel. I have a playlist about reproducing kernel Hilbert space. It's very important for future of machine learning. So given a collection of Q anonymous walk landmarks, the corresponding Q dimensional subspace is just the span of these Gaussians. And the projection of another anonymous walk onto E can be done like in this reference. So these are positive semi-definite matrix formed by kernel values. between Q landmarks. So we can also stack multiple layers to resemble a L-layer GNN. This is an overview of the architecture that combines two graph kernels, and one being RWGK and the other being AWGK. So nodes are projected into the reproducing kernel Hilbert space through the kernel mappings of both, which are formulated as GNN. The idea is very nice, but it is not bio-inspired. We should work on this idea to see how can we make it more bio-inspired. I mean, it should be a kind of a simulation, a process, like MCMC is a process, or random walk, a process. Then we have node level representation. So we have a graph level embedding, and then we have graph classification, and we have many papers like this. But I want to say that a machine is conscious if it is interpretable, if it can interpret why it has predicted such a estimation. Otherwise, it has learned spurious correlations, something that is not grounded on truth, and human cannot interpret it and understand it, and it is understanding false idea. But so there is a concept bottleneck paradigm, that we go from features, where elementary features like pixels of an image, to some concepts. Then from concepts we go to classification. This has better generalization. This has the noise will be removed easily if we go through this interesting paradigm, which is very bio-inspired as well. But sometimes here the question is, what is the how about the compositional concepts? Because the space is huge, so things like beam search and those things needs lots of memory. How do you deal with that? And that is another problem. But so you see all of these results that even if they get 100%, doesn't mean it is interpretable. But this is a really nice paper. I really enjoyed it.